So yeah, these slides, as you probably already know, are complete. I didn't take any words out of these slides. It's just the way it kind of historically worked out. But this actually, we've talked about our cosmological horizon, kind of like the edge of what we can see. And there's actually a couple reasons why we can't see beyond what we can see. One of them is because light takes a certain amount of time to travel to us. And the other is the concept of a Big Bang. Basically, our universe is expanding into nothingness. So but this actually is kind of the energy that finally got through the beginnings of the Big Bang. And we'll be talking more about this. That's pretty cool. So I think we already did this video, but I'll do this little video again. Those little, they look like mouse turds on that grid up there, but actually those are all galaxies. And the kind of the fabric, the grid lines you see there actually is the fabric of space and time. And so when I run this, you're going to see with regard to proximity, our universe has been expanding. And so if it's expanding now, if you go backwards, at one time it was smaller, okay? And you guys told me on one of your tests that the reason it was smaller is because, how do I say this? Oh yeah, one of the consequences of it being smaller was there was more interaction between those little nugget things. Those are actually galaxies. So when I play this, it's going to actually, you're going to see it go backwards in time. Now remember that when we talk about expanding universe, actually the fabric of space and time is expanding. Click there. Okay, this is running backwards towards the beginnings of our universe, because that's the fabric of space and time that has been expanding now. It's contracting because we're going backwards. And we said, honestly, we can date the beginning out of our universe using the fact that the galaxies are accelerating away from each other. That's Hubble's law. We can date it between 13 and 15 billion years ago. And if you're like me, you're like, what's the G? 15 G years, okay? G is giga, and actually that works with billion. So kind of prove that to yourself. Okay, so actually down here you see Hubble's, the graph of Hubble's law, where galaxies that are further from us are going faster away from us. So that's kind of something we talked about in the last chapter. Okay, so when we talk about density, of course, density is like, we've talked a lot about density. Normal density, white dwarf density, neutron star density, black hole density, okay? So a long time ago, the universe is very dense, okay? And it was very hot. And so if you plot those, or not plot those two parameters, but this is actually looking at the temperature of the universe. Temperature of the universe. You're like, how did they know that? Well, go ask an astrophysicist. I'm going to try to do my best, okay? How hot was the universe, okay? And this is actually going forward in time. How hot was the universe? And this is in units of seconds along the x-axis. So to kind of put this in perspective, okay, remember that in science we have to kind of use the scientific notation. So 10 to the negative fifth is what? 0.00001, okay, seconds. That's the way that works. 10 to the 15th seconds actually is in the ballpark of where we are today after the Big Bang, that kind of 13 to 15 billion years after the Big Bang. Okay, so yeah, the universe was very hot. So now temperature along the y-axis is in units of Kelvin, okay, that absolute temperature scale. Okay, so 10 to the 32nd is 1 with 32 zeros after it, Kelvin. That's how hot it was. 10 to the negative 45th seconds after the Big Bang. Okay, I just think that is so cool. No pun intended. So there's 10 to the 32nd Kelvin units. Okay, so the universe expanded. We're going to talk more about that expansion in this unit. But as it expanded, it cools. And honestly, that's the way physics works in today's world, today's universe. Things expand and they cool. Okay? So I mentioned actually over here-ish is where we are today. So this line right here is 10 to the 15th seconds. Okay, so somewhere between these two lines actually is 4 times 10 to the 17th seconds. Okay, that's where we are today. It's funny to think of time between the Big Bang and now in terms of not years but seconds. Okay, do the math. It is, and I've done the math. I'm like, really? Like, yeah, you can work that out. Factor label. Okay, so how cool is the universe today? The universe. Now that's a hard thing because, we're running about. Well, dang. Okay. Our bodies have a certain temperature. The Earth has a certain temperature. Our sun has a certain temperature. You're like, what is the temperature of the universe? Well, the temperature of the universe is running about 3 Kelvin, 3 units above absolute zero. Okay, and it's kind of cool how it's. Anytime you see a straight line in science, you're like, oh, that's awesome. Okay. So if that's the temperature of the universe, don't be alarmed. Actually, we are a fair bit above absolute zero. We're 298 Kelvin. That's about the Earth's temperature. Okay, and then of course people have different temperatures, and living people, dead people, etc. Okay. So the universe used to be a lot denser and a lot hotter. It cooled off. Okay, we're going to talk about that cooling off and that expansion. But see those the cute little blue E and the cute little red E? Those are both electrons, but one is matter and one is antimatter. The stuff you hear about in Star Trek, right? Okay. Honestly, that it's a real phenomenon, and it's been a while since I read the article, but they actually can create antimatter. It doesn't last very long because our world is matter, not antimatter. Again, it sounds like a Star Trek episode. I'm like, Captain Kirk, where are you? And it's true what they say in Star Trek, and we're going to actually see this in the beginnings of our universe unfolding, is that if matter and antimatter come in contact, they annihilate one another. So you're like, dude, that's not good if you're trying to build a universe. Okay, so Einstein said, actually, we've talked a little bit about this in lecture, that you can go back and forth between energy and matter, okay? The M term in E is equal to mc squared actually is the mass of the matter. So you can convert matter to energy and energy to matter, okay, according to that relationship. So early on, our universe definitely didn't have planets. Our universe definitely didn't have stars. Our universe did not even have atoms. It didn't have nuclei of atoms, okay? It was like soup. It was like energy particle soup. That's kind of what this is talking about. Okay, and this actually then is the Star Trek thing, the matter and antimatter coming together and annihilating each other, actually going back to form energy. So out of energy, which would be the gamma rays, okay, out of energy we can create matter. Oftentimes that matter is created in pairs, which then just goes ahead and annihilates one another. So you kind of had this back and forth sort of thing, early on in our universe. Like, dude. And you may have seen this figure before. It's a good one. So kind of starting from upper left to lower right, we have our Big Bang. Not this show, but the Big Bang, okay? And can you kind of see the texture in this part of the figure is kind of like what I said was the background of our early universe? Okay, that actually is kind of early baby pictures of our universe. And there's a time there, 380,000 years after the Big Bang. So actually you're going to see that's an important time, okay? And the cooling process and the time process of our universe. Then after that, it's all like, oh, we know this, okay? So you can actually see, when we talk about eras here in a minute, and I don't know if we'll get to it today, it might be on Friday, but we are in the era of galaxies, galaxy building. So it's a wonderful time to be around. And you can kind of see that in this figure. So physicists, I don't know, I'm not a physicist, but I'm kind of back and forth between, what we are now, what our universe is now, kind of going back and what it was before. And what it is now is we have 4 forces, and we're going to talk about those 4 forces, okay? And what it is now is we have normal matter. We have, this table is made up of carbon atoms, hydrogen atoms, oxygen atoms. Okay, probably, I guess it's plastic, isn't it? So anyway, not necessarily cellulose, but we're used to atoms making up molecules. That hasn't always been the case, like I said a minute ago. Okay? And as we talk about from the Big Bang to how we are now, we have to kind of talk about those four forces that we know now, what were they then, and kind of the matter that we know now, what was it then. Okay, and we're going to talk about, I can't remember how many eras there are, but we end in the era of the galaxies, which is awesome. But there are several eras that we're going to talk about, and they differ by terms of what were those four forces doing and what were the particles doing. Okay, so the four forces that we have now and we have to account for then was the force of gravity, the force of electromagnetism, and these last two you may or may not be familiar with. They're kind of associated with an atom. Okay, the weak force and the strong force, which seems kind of strange. I'm going to go ahead and play you a little video because we're all kind of familiar with gravity, okay? And, you know, if you rub a balloon on your hair, you got the whole kind of electricity going on. You can kind of see how things are attracted. That's electromagnetism. But the weak and the strong force, I'm going to kind of let this video speak for it. All right, so four forces as they are today. Now, here's a figure, and this is one of the things, and I like the figures in your textbook, but it goes backwards compared to the figure we just saw. So this is to say that time is actually, this is the Big Bang, and then this actually is today. Okay, so it's going back. And actually you can see that because we said that we're at what, we're at 4 times 10 to the 14th or so seconds after the Big Bang. So it's kind of going, no, that's not seconds, hang on. Temperature, okay. But it's going backwards. Oh, there's time at the top. So this actually isn't even 1 complete second after the Big Bang. Okay, so let's look at those four forces. So right now, like I said, we have four forces. We definitely have gravity, we have electromagnetism, we have the strong and the weak force associated with those cute little atoms that go together to make compounds and that we count on for so much. Okay, so that's what we have today. But notice that actually it wasn't just even a fraction of a second after the Big Bang. So this is going towards today. So today's clear up here. Okay, that we had those four forces. So what happened actually in just like the fraction of a second after the Big Bang is a lot. Okay, so scientists can, going backward, actually see where the weak force associated with the atom and the electromagnetic force actually used to be a common force called the electroweak force. Okay, and then going back even a little bit further, those two forces combined with the strong force also associated with an atom. And so we had what's called, or they have called, what's called a gut force, GUT force. So the gut force, if you hear astrophysicists or whatever talking about it, that's actually 3 of the 4 forces that were combined together clear back near the beginning of time, as we know it, our universe. And notice the lone guy, the force of gravity. Okay, he kind of was not, but actually the next slide says, was gravity part of those other 3 forces? Possibly. When you hear them talking about the unifying the 4 forces, this is what they're talking about. So the thing along the both axes, the x-axis on both the top x-axis and the bottom x-axis is time and temperature, because we said that actually as time unfolded after the Big Bang, it started cooling down. That's kind of what you see here along the bottom x-axis. Okay, so the y-axis is just kind of showing you them separating or them coming together. So there's the same figure. And so, like I was saying, going back in time towards the Big Bang, the electromagnetism and the weak force combined together, they call the electroweak force. You throw in the strong force, makes 3 then, called the gut force. And then, as I was saying, was gravity ever part of, was it ever combined at those high temperatures with the other 3 forces? And possibly. If you've ever heard of string theory, I think that's been out for maybe 15, 20 years now. There's a video, it's been out, gosh, has it been 10 years now, called The Elegant Universe? It's a great video, a documentary talking about string theory. And it's awesome. But I hope you get a sense for it matters. We have something today. The four forces are separated. We're at a certain temperature. But it does make a difference for our understanding of what those forces are today is what they were back then. Okay. So now we're going to talk about the eras. I thought we were going to do that today. Yeah. So the eras are kind of like the stages of, the stages of your life. You're an infant, a toddler, an adolescent, young adult. I don't know. But it's our universe. Okay, and you might already get a sense for a lot happened in that first fraction of a second. So we're going to be dealing with a lot of fractions of a second after the Big Bang. The first era is called the Planck era, and actually it ended at, well, what I did was down here to unpack that 10 to the negative 43rd. I know. This fraction of a second is when the Planck era ended. Okay. And you can see the temperature exceeded 10 to the 32nd kelvins during that time. Okay. All the forces may have been unified, possibly string theory. Okay. So this is like Big Bang to 10 to the negative 43rd seconds. That's the Planck era. And I think on that review sheet that I gave you for your unit exam, it says something about eras. And I think it would probably, and on your review I'll remind you, just make sure that you jot down the eras. Planck era is the first one. Okay. Then followed by the gut era. And so remember the gut era, clearly we had three forces that were together, not gravity, so that was the other three forces together. Okay. It's the universe is cooling down. Okay, gravity is distinct. We need gravity to kick in before we can finally get, ultimately, stars or galaxies, right? Okay. And this says actually that this gut era ended when finally the strong force broke out away from the electromagnetic and the weak force. Still very hot. We're going to talk on Friday about this phenomenon called inflation. Inflation isn't necessarily an era. Inflation is a phenomenon. And if you think of you inflating a balloon, the balloon's getting larger. I think that's probably where the word inflation came from. But inflation is an important aspect associated with our current theory of the Big Bang. Okay, and that actually happened, I think it looks like at the end of this era, the gut era. A gut era. Okay, again, these are fractions of a second. Okay, the next era after the gut era, this is getting closer to present day, still a fraction of a second, is the electroweak era. Okay, so here we definitely have the strong force broken away from its other buddies that were part of the gut force. And I haven't mentioned it. Oh, well, I guess this is the first little box. See, finally we have a little box here. Okay, this little box is talking about the soup of particles that are present at that time in our universe. We have a soup of particles, definitely not atoms, but finally we have a soup. Notice the little boxes in the other. They're like, I don't know. What did matter start to look like? And the way it's been explained to me, and I think we'll see it on this video, is basically our universe used to be, when it started, unfolded at the time of the singularity, it was basically one big ball of energy. It's kind of like you watch those science fiction movies where, and I can't remember which one I was watching. I think it was like the American, I don't know, but they're after that one big ball, one small, in that case, ball of pure energy. And that energy was converted into matter, according to E is equal to mc squared. But we're going to see it was actually converted into matter in pairs, matter and antimatter. So finally, when temperatures cool sufficiently, okay, and this is still up to 0.001 seconds after the Big Bang, finally we have temperatures that allow what we would matter that's what we generally think of today, okay, the particle era. Now this particle era, it's not cool enough for us to go ahead and have atoms, okay, let alone molecules. Okay. And this actually is talking, this is the cool part, it says amounts of matter and antimatter are nearly equal. And what does matter and antimatter do, Captain Kirk? Okay, they annihilate each other and release a lot of energy. Okay, so if they're equal, you're like, oh, we don't have a universe yet. Okay, but this says, hold on, because actually you have just a little bit more matter, you have a little more protons than you do antiprotons. Okay, so that's why we ended up with the world we have, the universe we have, instead of an anti-universe. But I've heard it described, actually, the physics would favor the antimatter as to the regular matter, so I don't know. It's interesting, though. Okay. So one of the things we talked about in this course was the structure of an atom. So finally, we're going to start to kind of build things after the particle era. Things are cooling down to hopefully building some atoms. And at the center of an atom is a nucleus. Okay, and so this era of nucleosynthesis, anytime you see the word synthesis in science, they're saying assembling, right? So nucleosynthesis is starting to kind of build those nuclei of those things that are going to be atoms ultimately. Why? Because it's cooling down, okay? And energy, it's cooling down because it's expanding and energy is being converted into matter. Okay, so this is a good thing. After the era of nucleosynthesis comes related to that, then comes the era of nuclei. Again, I just draw all these on your note card. Okay. And so if you kind of compare, the pictures look very similar. I'm trying to see. I think if you read the description between the era of nucleosynthesis and the era of nuclei is you can finally start to get a little more complicated nuclei. If we consider elements, atoms of different elements, of course hydrogen is the simplest element, and after hydrogen is helium. So actually once you're starting to get a little more helium nuclei. One of the things I want to point out before I go on to the next era is that, do you see kind of the orange there? Okay. That orange means that, and actually that orange is created by, see those kind of dots, those kind of the blue and the dot, the white dots and the blue dots. Okay, those are kind of like, I think it says in the caption, free electrons moving around. Okay, and actually these free electrons did a good job of basically, if there was any sort of radiation that wanted to escape from their vicinity, those free electrons do a good job of saying, no, you don't. You're not going anywhere. So then finally, this is exciting. To me then, I go back to the electrons. When the electrons finally said, okay, I'm going to settle down with one nucleus. When an electron settles down with a nucleus, guess what? You got an atom. Okay, nucleus, electron, you got an atom. And in doing so, it kind of, you see the picture went from kind of orange to blue, sky blue clear. Okay. So, and you're going to hear them talk about this era, and check out the date here. It's like 380,000 years after the Big Bang. That actually, on the figure we saw a little bit ago, was a key date. It's a date where they say the universe became transparent. Okay? And it didn't, I can't imagine it will happen just like this. But it happened because atoms were basically formed. Electrons found homes around nuclei. And I'm going to go ahead and add something to this slide. Anytime you hear people talk about, and I think the videos hopefully will speak for themselves, but anytime you hear people talk about the cosmic microwave background, and I bet it's on maybe even the next slide, otherwise called the CMB. Well, if you break it down, you probably see the word microwave. And I have a slide to remind you that actually microwave is just one cousin of the family of energies we call electromagnetic radiation. So microwaves are clear down here, okay, because we have visible, radio, microwaves. They're just long energies. So when we talk about looking at our cosmological horizon, I'm going to kind of hopefully explain why this is. When we talk about looking at the edge of the universe, our seeable universe, we are actually going to see these long wavelengths that were just finally cut loose after this era. It's just so exciting. I cannot overemphasize how exciting that is. Okay, so we had the era of atoms, and then kind of in that vicinity, so that was what, that began 380,000 years after the Big Bang. And then just 1 billion years, well, I guess that is quite a difference. Okay, so after atoms, then we're finally going to go ahead and within those atoms are going to, it's not a straightforward process where those atoms finally come together to create stars. We've been talking about that earlier this semester. Definitely not a simple thing. Okay. So yeah, 1 billion years after the Big Bang, you finally got your first galaxies. And we looked at baby galaxies before. Those baby galaxies look kind of rough, don't they? Galaxies now, some 13 to 15 billion years after the Big Bang, we're kind of settled down into some beautiful spiral galaxies and that sort of thing. So we are currently in the era of galaxies.
I have a question. These little words about them on the side, would that be what you want, kind of on our note card? This kind of information?
I'll double check, but the question and the final, I haven't put together the final yet, but I really think it's just list the eras. Yeah.
Okay, I didn't know if you wanted to know what era or what happened in each era.
To me, though, I guess I probably would, next to it, because you have room, just say, a few words, what was significant about that era.
Okay.
I probably would. So I'll probably, in fact, I would. But I can't, I don't know.
Okay, I just didn't know if this kind of stuff on this that you have on the side would be.
Almost within the name, it kind of says what happens, but yeah.
Okay.
I don't know how to answer that. So, all right. So on Friday, we'll talk more about this, both of these aspects. But I mentioned, and it goes along with what I said earlier, if this is the Big Bang, I can't remember which way I did it, and this is today, okay? We have to kind of go backwards, obviously. And so things that we observe today that support kind of the current theory of, not kind of, but the current theory of the way our universe unfolded are here. Okay, one is that kind of that orange picture you saw a little bit ago, that cosmic microwave background. That's what that is. Okay, basically they call it the hiss from the beginning of the universe. That's one evidence. And then the other is, and we'll talk more about this on Friday, the fact that when we gauge our universe, not the Earth and not our solar system, but when we look at the universe and we look at how abundant or how much of the different types of elements there are, the relationship between the amount of hydrogen and helium we have in the universe actually says, yeah, it's consistent with the current theory of the Big Bang. All right. I think I'm just going to go ahead and play this little video, but don't they look proud? They won, I'm thinking a Nobel Prize in physics for actually using the device they're standing in front of, which looks kind of cheesy, but by today's standards. In everyday life, you guys do a lot of troubleshooting, I'm sure. Trying to narrow down, is it this or is it that? That's kind of what science is. And the thing about in everyday life, if you're troubleshooting and in science, is you have to believe your eyes. You cannot take the data and say, well, I think it's wrong, if your eyes are telling you something. Okay, so that's pretty cool, pretty cool. So I actually brought this figure. I don't know if you have it in your packet of slides, but this is a figure from way back when we talked about the different cousins of electromagnetic radiation. So just to kind of put it in perspective, what they were seeing actually, and I got it wrong a minute ago when I said it was visible, I think I said radio and microwaves. Actually, microwaves are between radio and infrared's longer than visible. Okay, so you can kind of see the energies that they were seeing. Okay, So, I can't remember. All right, so remember the slides with the orange and then the slides with the blue, okay? The difference between them was basically, like I was saying, the electrons kind of settling down. And when that happened was basically 380,000 years after the Big Bang. Okay, and so that's finally when we could actually have a hope of seeing anything. And the reason of that is, I'm going to play this little video for you, is actually the little energies would kind of bounce off or interact with the electrons. So they needed to settle down. That's all this one does. It's a short one. You can kind of see the temperature cooling. I think it was at 3,000 Kelvin is the sweet spot where those little blue things are electrons connect up with nuclei, and you get atoms, the air of atoms, and there you go. So that energy's been humming around in all directions, including the direction of us and Penzias and Wilson ever since. It's kind of a disturbing little video because it shows that it doesn't show any motion with the atoms, but that's okay. I mean, yeah. So we talked about black body radiation curves in here, and we said basically they are a fingerprint of a temperature. And so all things considering the current theory of the Big Bang, you saw a little bit ago that the universe should be running about 3 Kelvin, okay? And so actually this is kind of going back to that idea. Not only that, but this kind of hurts my brain to think about it, but remember we said that there's something called cosmological redshift. There's a lot of redshifts, right? Things are getting redder because wavelengths are getting elongated. But when the fabric of space and time gets larger, okay, actually then the signals from that we're looking for actually would get longer too. I like this one. See what you think. Yes, it's safe.